Today's topic of discussion is for damped vibration and critical speed of rotor on flexible bearing supports. So in this section, I will discuss about the damped vibration of rotor on flexible bearing support, where rotor equations, bearing equations are derived, and then damped critical speeds are derived, and finally see the amplitude of the bearings as well as the rotor. So let's begin the discussion. These are the main points for damped critical speed on flexible bearing support. Bearing is considered flexible and hence displacement of shaft at bearing and also bearing displacements are considered, but the mass of bearing is not considered as it is smaller than mass of shaft and hence neglected. Damping of shaft is not considered being a smaller value, but the damping of bearing is considered as it is a discussion of damped condition. Derivation of critical speeds, derivation of amplitude of our bearings, amplitude of shaft, understanding of bearing damping, then various curves for the speed versus amplitude for bearing, rotor, and where the curve for amplitude and where in x and y direction for different values of damping ratio and stiffness. So a rotor is supported on flexible bearing, bearing number 1 and bearing number 2, and as bearing is considered for flexible, so there will be displacement of shaft at bearings as well as the displacement of bearing itself. But these displacements are perpendicular to the direction of rotation of the shaft. So let's understand about the derivation part of damped vibration of rotor. So let's assume the following: the mass of bearing is neglected, damping of shaft is neglected, then mass at center of shaft is mkg, the stiffness of shaft is K1 Newton per meter, the stiffness of bearing is K2 Newton per meter, damping of bearing is C2 Newton second per meter, eccentricity of mass from the center of axis is EU in meter, angular speed of the shaft is omega radian per second, angular displacement in time t is equal to omega t in radian, lateral displacement, if lateral displacement of the shaft and bearings are x1 and x2 respectively in x direction and y1 and y2 respectively in y axis, then shaft equation in x direction can be written as m into x1 double differentiation plus k1 into bracket start x1 minus x2 bracket close is equal to m into EU into omega square cos omega t. Similarly, for the shaft equation in y direction, m into y1 double differentiation plus k1 into y1 minus y2 bracket close is equal to m into EU into omega square into sine omega t. Bearing equation in the x direction, c2 into x1 differentiation plus k2 into x2 is equal to k1 into bracket start x1 minus x2 bracket close. Similarly, for the y direction, bearing equation can be written as c2 into y2 dash or differentiation plus k2 into y2 is equal to k1 into bracket start y1 minus y2 bracket close. If Z1 and Z2 are the complex number of the shaft and bearing displacement respectively, then equation of motion of the shaft for complex number form can be written as shaft equation is m into Z1 double differentiation plus k1 into Z1 minus Z2 bracket close is equal to m into EU into omega square into bracket start cos omega t plus I sin omega t bracket close. But e to the power I omega t is equal to cos omega t plus I sin omega t. So shaft equation can be written as m into z1 double differentiation plus k1 into z1 minus z2 bracket close is equal to m into eu into omega square into e to the power I omega t. Then bearing equation can be written as c2 into z2 differentiation plus k2 into z2 is equal to k1 into bracket start z1 minus z2 bracket close. So these are two expression for motion of shaft equation as well as the bearing equation in the damped condition on flexible bearing support. Now damped critical speed. So same way shaft equation is written as m into z1 double differentiation plus k1 into bracket start z1 minus z2 bracket close is equal to m into eu into omega square into e to the power I omega t. This is equation number 1. Bearing equation c2 into z2 dash or differentiation plus k2 into z2 is equal to k1 into bracket start z1 minus z2 bracket close. This is equation number 2. For natural frequency or critical speed, external forces will be 0. That means this term will be 0. So shaft equation can be written as m into z1 double differentiation plus k1 into z1 minus z2 bracket close is equal to 0 is equation number 3. Assume the solution of the form rotor displacement is written as z1 is equal to z3 into e to the power I sorry z1 is equal to z3 into e to the power lambda t, where z3 is equal to displacement in complex number and lambda is eigenvalue and t is the time. Similarly, bearing displacement is z2 is equal to z4 into e to the power lambda t, where z4 is a displacement in complex number, lambda is eigenvalue and t is the time. So z2 dash or z2 differentiation is equal to z4 into lambda into e to the power lambda t, and z1 double differentiation is equal to z3 into lambda square into e to the power lambda t. So after replacing z1 double differentiation, z2 and z2 differentiation in equation number 2 and 3 can be written as bracket start m into lambda square into z3 plus k2 into z3 minus z4 bracket close whole bracket close into e to the power lambda t is equal to 0. And for second equation we can write bracket start c2 z4 lambda plus k2 z4 bracket close into e to the power lambda t is equal to k1 into z3 minus z4 bracket close into e to the power lambda t. But e to the power lambda t cannot be 0, and so below are the equation. On simplification we can write m into lambda square into z3 plus k1 into z3 minus z4 bracket close is equal to 0. This is equation number 4. And c2 into z4 into lambda plus k2 into z4 is equal to k1 into bracket start z3 minus z4 bracket close is equal to sorry, this is equation number 5. So by definition, a standard damping C0 is equal to 2 into a square root of K1 into M, which is equal to 2 into M into a square root of K1 upon M, which is equal to 2 into M into omega CR, where omega CR is undamped critical speed on rigid bearing support. Rigid bearing support, not rigid rotor. It's a rigid bearing support. By mistake, it is written rigid bearing support. So after replacing, and then bearing damping ratios zeta 2 is equal to C2 upon C0, and so C2 is equal to 2 zeta 2 M omega CR. So after replacing C2 in equation number 5, we can get 2 into m into omega CR zeta 2 lambda into Z4 plus K2 into Z4 is equal to K1 into Z3 minus K1 into Z4. So Z3 is equal to 2 into m into omega CR into zeta 2 into lambda upon K1 plus 1 plus K2 upon K1 bracket close into Z4. But stiffness ratio K is equal to K2 upon K1 and omega CR is equal to a square root of K1 upon m. So we can write Z3 is equal to 2 into zeta 2 lambda upon omega CR plus 1 plus K bracket close into Z4. This is equation number 6. From equation number 4 we can write m lambda square plus K1 bracket close into Z3 minus K1 into Z4 is equal to 0. So we can write lambda square plus K1 upon m bracket close into Z3 minus K1 upon m bracket close into Z4 is equal to 0. So further we can write lambda lambda square plus omega CR square bracket close into Z3 minus omega CR square into Z4 is equal to 0. This is equation number 7. So after replacing Z3 from equation number 6 and 7, we can putting all the value, we can on simplification we can get 2 into zeta 2 lambda q plus lambda square omega CR into bracket stand 1 plus K bracket close plus 2 lambda zeta 2 omega CR square plus K omega CR cube is equal to 0. So this is a cubic equation for damped natural frequency on flexible bearing support. An imaginary part consists two damped natural frequency, one forward and another backward natural frequency. The forward natural frequency is a damped critical speeds. So this is a cubic equation, and you on solving this you can get damped natural frequency or damped critical speed. Now damped vibration amplitude of bearing. So again the shaft equation m into Z1 double differentiation plus K1 into Z1 minus Z2 bracket close is equal to M into EU into omega square into e to the power I omega t. This is equation number 1. Bearing equation C2 Z2 differentiation plus K2 Z2 is equal to K1 into Z1 minus Z2 bracket close equation number 2. So assume solution of the form rotary displacement Z1 is equal to Z3 into e to the power I omega t, and bearing displacement Z2 is equal to Z4 into e to the power I omega t. So Z1 double differentiation is equal to minus Z3 omega square e to the power I omega t, and Z2 differentiation is equal to Z4 I omega e to the power I omega t. So after replacing Z1 double differentiation and Z2 in equation number 1, we can write m into minus omega square into Z1 plus K1 into Z3 minus Z4 bracket close is equal to m into EU into omega square. So after dividing by K1 and putting omega square is equal to K2 K1 upon m. So on simplification directly we can write bracket stand 1 minus f square bracket close into Z3 minus Z4 is equal to EU f square. This is equation number 3. So after replacing Z1, Z2 and Z2 dash in equation number 2, we can write C2 I omega plus K1 plus K2 bracket goes into Z4 is equal to K1 into Z3. So again by a standard definition, we can write C2 is equal to 2 omega 2 zeta 2 m omega CR. So after replacing C2 in the above equation, we can write on simplification 1 plus K into I 2 zeta 2 bracket close into F bracket close Z4 is equal to Z3. This is equation number 4, where K is a K2 by K1 stiffness ratio. So after replacing Z3 from the equation 3 and 4, and we can write this equation: Z4 upon EU is equal to F square upon K minus F square into 1 plus K bracket close plus I into 2 into zeta 2 F into bracket 1 minus F square bracket close. So let's magnitude Z4 is A2 and A2 is a displacement from 0 to peak. So we can write A2 is upon EU is equal to F square upon square root of bracket start K minus F square into bracket start 1 plus K bracket close whole square plus bracket start 2 zeta 2 F into bracket start 1 minus F square bracket close whole square 2. So these are the expression for amplitude of the bearing. So when speed omega is equal to undamped critical speed omega CR, undamped critical speed on omega C, and so F is equal to, we can write omega is equal to omega CR. So we can write omega C of omega of C by omega CR can be written as square root of 1 K upon 1 plus K. So after putting this equation, we can write A2 upon EU is equal to F square upon 2 into zeta 2 into 1 minus F square bracket close. So on simplification, we can write A2 upon EU is equal to square root of K into bracket stand 1 plus K bracket close upon 2 zeta 2. So these are the amplitude at critical condition. Now damped vibration amplitude of the shaft. So shaft equation again m into z1 double differentiation plus k1 into bracket start z1 minus z2 bracket close is equal to m into u omega square e to the power I omega t. This is equation number 1. Bearing equation c2 into z2 differentiation plus k2 into z2 is equal to k1 into bracket start z1 minus z2 bracket close. This is equation number 2. Same way, assume the solution rotor displacement z1 is equal to z3 into e to the I omega 2 and bearing displacement z2 is z1 and bearing is z2 is equal to z4 into e to the power I omega t. Again putting z1 z double dash and z2 in equation number 1, we can write simplify this 1 minus f square bracket close z3 minus z4 is equal to eu into f square. This is equation where f is a frequency ratio and omega CR square is equal to Q1 upon M. So after replacing Z1, Z2, Z2 dash in equation 2, we simplify C2I omega plus K1 plus K2 bracket close Z4 is equal to K1 into Z3. So again bearing damping ratio zeta 2 is equal to 2 omega 2 zeta 2 M omega CR. So after replacing C2 in the wave equation, we can write 1 plus K plus I2 zeta 2 F bracket close Z4 is equal to Z3. This is equation number 4. So after replacing Z4 from the equation 3 and 4 and on simplification we can directly write this equation Z3 upon EU is equal to F square into 1 plus K plus I into 2 zeta 2 into F bracket close upon this one K minus F square into 1 plus K bracket close plus I 2 zeta 2 F into 1 minus F square bracket close. So let's say Z3 is A1 and A1 is displacement from 0 to peak, so we can directly write in magnitude A1 upon EU is equal to F square into a square root of 1 plus K square plus 2 zeta 2 F whole square bracket close upon a square root of bracket start K minus F square into 1 plus K bracket close whole bracket square plus 2 zeta 2 F into bracket start 1 minus F square bracket close whole bracket square. So these are the expression for shaft amplitude. On critical condition, we can write directly for shaft A1 is upon EU is equal to a square root of square root of k plus 1 square upon square root of 1 plus k square plus 4 zeta 2 whole square into k upon 1 plus k upon this one. So when putting this value, f is equal to omega c square at critical conditions. Now bearing damping. So bearing damping of each bearing in x direction is cxx, and bearing damping on each bearing in y direction cyy Newton second per meter. Average damping of each bearing is Cv is equal to half of Cxx plus Cyy. Bearing damping of both bearing is 2 times, that is 2 times of Cv. Let's say Cxx Cyy are 110 into 10 to the power 3 and 120 10 to the power 3 Newton second per meter respectively, and rotor has a model mass 360 kg and a shaft stiffness 6 into 10 to the power 7 Newton per meter. Calculate the bearing damping and bearing damping ratio. Cxx is 110 into 10 to the power 3 and Cyy is 120 into 10 to the power 3 Newton second per meter. M is 360. Shaft is stiffness K1 is equal to 6 into 10 to the power 3, sorry, 10 to the power 7. Average damping ratio half of this, which is 115 into 10 to the power 3. Bearing damping both bearing 2 times, which is 230 into 10 to the power 3 Newton second per meter. A standard damping we can write 2 into square root of K1 into M, which is on calculation 293938.8. So bearing damping ratio zeta 2 is equal to C2 by C0, which is coming 0.7825. Now damp vibration speed versus amplitude curve. So these are the bearing damping, and you can see on x-axis is speed, y-axis is bearing amplitude, and you can see at the critical condition the amplitude is a maximum. Similarly for the shaft amplitude, x-axis is a speed and y-axis is shaft amplitude. Again at critical condition the amplitude is a maximum. Now the bearing amplitude in x and y direction with a different value of damping value, you can see the two different amplitude at two different damping values and bearing stiffness, because x-axis is speed and y-axis is amplitude of bearing. Similarly for the shaft amplitude in x or y direction, x-axis is speed and y-axis is amplitude of the shaft. Similarly for the different damping of the bearing and stiffness, see we have two different curves. So thank you. Hope you have understood about the damped vibration of rotor on flexible bearings and the derivation of the motion of the shaft, and for the motion of the bearing then finding out critical speed, which is a cubic equation, and finally we have to see the amplitude of the bearing and amplitude of the shafts. So hope you like this. Thank you for watching.